Okay, last time we derived Gauss's law, which you'll recall is the first of Maxwell's equations, and it says that the electric flux through a closed surface, so the electric flux is always defined as the integral of vector E dot d vector A, but putting the little circle on the integral sign means the electric flux through a closed surface is equal to the net enclosed charge divided by epsilon naught. And I'll just remind you that epsilon naught is defined to be 1 over 4 pi k, where this is the k that appears in Coulomb's law. There are two main classes of applications of Gauss's law. The first one is finding the electric field due to a symmetrical charge distribution. And the second one, which we'll talk about later in this class, is making several qualitative but very important arguments about electric fields in and around metals, i.e. electrical conductors. So by symmetrical charge, I mean either charge that is spherically symmetrical, that is, the charge is distributed within a sphere, or perhaps a series of concentric spherical shells, cylindrically symmetrical, spherically symmetrical, cylindrically symmetrical, or planar symmetry. And we'll discuss examples of each of these different types of symmetry. This application is very, very important, and certainly you should expect this to appear on your exams. So let's do an example of this, and with this example I will illustrate a multi-step procedure. The example is going to be finding the electric field due to an infinite rod of charge. So let's set things up. I've got a rod that is very thin, and it's infinite in extent, and all along its length it's got charge with a uniform charge per unit length. This is the Greek letter lambda. So lambda is the charge per unit length, and so since it's charge per length, the units would be coulombs per meter. So for example, if lambda is 0.5, then a 10-meter length of the rod would have 10 meters times 0.5 coulombs per meter would be 5 coulombs of charge in it. So the total charge in the rod is infinite because it's infinitely long, but the charge per unit length is finite, lambda. I'm going to pause here and we'll pick it up in the next segment.